Last class we were talking about refraction of light. We mentioned that refraction is the bending of light or waves when passing from one medium or material to another. And we talked about how, right, there is, like, if it's moving from an optically dense moving entering an optically dense medium, sorry, so moving from air to glass, it will bend towards the normal to the surface of the medium. It is, if light is going from an optically dense medium to an optically less dense medium, so it's moving from glass to air, it will bend away from the normal. And then a ray emerging from a parallel sided block is parallel to the ray entering, but it is displaced sideways. So it's traveling in the same direction at the same angle, but it has been shifted. And a ray traveling along the normal direct at the boundary is not refracted, so it just passes straight through. Right, then you've got the angle of refraction, which is the angle between the refracted ray and the normal. You've got the refractive index, which is the ratio of the sine of the angle of incidence to the sine of the angle of refraction, so that thing. And you have, right, what's happening is that the speed of light changes, right? So it's 3 into 10 to the power 8 uh, in air, and then, right, it's 2 into 10 to the power 8 in glass. So it's slower, right, or gets faster. So there's a change of speed traveling in that particular medium, and that causes the refraction, right? Similar to water waves, where the speed changes when water goes from deep to shallow. The waves actually get slower. In shallower water, the waves are faster. In deeper water, right? So the speed changes, right? And that also causes diffraction, refraction and diffraction. Well, not refraction, refraction. Right, now continuing today, we're going to talk about something called the critical angle. So what is the critical angle? Now keep in mind that this situation occurs only when light is passing from an optically dense medium to an optically less dense medium, right? And this is linked with another phenomenon called total internal reflection. So we'll talk about that, right? So when light passes from an optically dense medium to an optically less dense medium. And so, right, what we're basically talking about, for example, is going from glass, not grass, sorry, glass to air. And as we just reviewed, we know that the refracted ray will bend away from the normal. Right, so if I try and illustrate this over here, I mean, obviously I can very well do this. This guy, drag and drop. Okay, let's do that. Okay. In fact, this is glass, right? Let's use this guy. Okay. And so what you have is you have, right, the light coming in at a small angle, right? So this is around 74 degrees. Let's change the color. Sorry, it's yellow. So 73 degrees now. Anyway, point is, right? And so when it leaves, it's going to be refracted, right?
Yeah.
Now, what happens is, right, when in this scenario, when light is passing from an optically dense medium to an optically less dense medium, and I should probably get rid of this part. Yeah, so the light's just, in the glass and then moving out into the air. What happens is that there's a strong refracted light, and then there's a weak light that is reflected internally. Oops, need that guy again. All right, so what's 90 plus 70?
Hmm. 160.
Hmm. So where do I put this? Nowhere. This is, yeah, 180, 270, and then 270 plus 70 is, yeah, no. Anyway, right, you get a weak reflected light. So this is, right, your incident ray. This is your refracted ray, right? And this is a weak reflected ray. Now, as you increase, so you'll need another one. As you increase the angle of incidence, right? So the angle of incidence is here, right? This is the angle of incidence, and this is the angle of refraction. So what happens is when you are increasing the angle of incidence, the light, that the ray that is refracted keeps bending away from the normal until you reach a point where, right, light is coming in at an angle. So let's say it's coming in like this, and what's happening is that the refracted ray is at 90 degrees to the normal, right? And then you obviously have, right, a reflected ray as well. Now the angle at which this happens, right? So you have the normal over here. So this is 90 degrees, right? This is obviously the refracted ray.
That's the incident ray.
Yes, and this is the angle of incidence. So I, right, and the incident ray and the reflected ray, right, being reflected within the glass, right? So the angle of incidence, the angle of incidence at which the refracted ray,
I'm sorry to interrupt, sir, but somehow on the way when you speak, your voice gets muffled.
and probably is
Yeah,
the
now it's better.
connection, I'm guessing.
And now it's better.
Huh.
Yeah.
Okay, so when the angle of incidence at which the refracted ray is at 90 degrees to the normal, right, and moves along the boundary between the two media, is called the critical angle, right? Now, hopefully the yellow line is clear enough for you, right? And so,
Yeah.
right, basically what you're getting over here, what you do over here, and I'm going to remove the I, and I'm going to replace that with a C, right, where the C stands for critical angle, right? And we're not done yet, right? So light moving from glass to air or any optically dense medium to optically less dense medium, you keep increasing the angle to an extent that the refracted ray is at 90 degrees to the normal. Then if you increase it further, right? So we need another box like this. And so this time what's happening, right, is that you increase the angle slightly above the critical angle. And what you get is all the light being reflected inside. There is no refraction.
So the light is basically trapped inside?
I mean, that makes the light sound, oppressed. So it is
Yeah.
trapped, but you could say that,
Okay.
right? And so this situation, right, there is no refraction happening. There's no refracted ray. And this scenario is called total internal reflection. Okay?
Yeah.
So it is reflected inside the denser medium itself.
Yeah. Okay.
So, right, by proper definition, total internal reflection occurs when a light ray does not cross the boundary between the two media. right? It is totally reflected, as the name suggests, at the boundary. Is that clear?
Yeah.
Right. So where does this happen? Have you ever experienced this? If you've ever traveled, and Sobi, I'm sure you've experienced this definitely. You're traveling on the road, it's a long stretch of road, and in the distance it seems like there's water,
Okay.
a mirage as it's called. Have you ever experienced that?
Yeah.
Right? That
Yeah.
is that is total internal reflection happening.
Wait, say that again.
That is total internal reflection happening.
No, the example that you give.
The mirage, right? So when you're traveling on a road,
Yeah.
and in the distance there seems to be water on the road,
Yeah.
but when you get close there's nothing,
Oh, okay. Yeah. Yeah. Yeah.
right?
Yeah.
That is total internal reflection,
Oh, okay.
right? So
Yeah.
there's no real water on the road. It's just right. So why that happens, it's like somewhat explained in the text. You can refer to that. But
I,
yes, this has you know this happens in real life, and it has effects. So if that's clear, just that concept of total internal reflection, like we talked about the uh, refractive index. Right, now we're going to bring the refractive index and critical angle together. So
yeah.
what we know is the refractive index is the sine of the angle of refraction over the sine of the angle of incidence, right? Now
Yeah.
in case of the critical angle, right? So for critical critical angle, right? R equals to 90 degrees, right? And I equals to C, which is the critical angle, right? So the angle of incidence is the critical angle. So we can rewrite this by sine 90 over sine C. Are you following?
Yeah.
Right? Then from a bit of trigonometry, we know that sine 90 equals to 1. So then we have n equals to 1 over sine C.
Okay. Yeah.
Right? So we are talking about the refractive index. So how is this helping us, right? Now it helps us if, for example, we know the refractive index, right? So for example, the refractive index of some material is 3 upon 2, right? If n equals to 3 upon 2. So we can use that and we can say, oh, 3 upon 2 equals to 1 over sine C. Therefore, sine C equals to 2 upon 3, right? Therefore, the angle C equals to the sine inverse of 2 upon 3, which is 42 degrees. So for whatever media that we are comparing, the critical angle in that case is 42 degrees. So if we, right, I mean, we are still working, the basic concept is the refractive index that we talked about, right? And so critical angle is obviously something that occurs with the refraction of light, right? So
Yeah.
we're just applying the refractive index in the scenario where we have the critical angle, and finding the critical angle, right? So finding the refractive index, as I told you, the refractive index for a certain media is sort of a property of that media, right? So you can conduct experiments with refraction at different angles and find the refractive index. And then, right, even if you're not able to find the critical angle experimentally, you can find it theoretically.
Yeah. Okay.
Okay,
Yeah.
is that clear, Aram?
Yeah.
Okay, then there's few things that I'll just take you to the book for, right? It's not technical, so
Sorry?
that's why. Of course, if you need further explanation for that, then we'll do that. We'll go over it. So can you see the book?
Yeah.
Right. Now, I don't know if you've ever experienced this, but right, have you ever seen reflections happen this way? They look hazy, and then they look like there's more than one reflection happening. Have you ever experienced this?
Yes.
Yes, but for me it wasn't that intense. I still have the image.
Right. So, right, this is multiple images happening in a mirror. So what happens is, right, you can either have, right, what they do is that they make a silver coating on the glass surface, and that is what helps reflect the light. That is what makes a mirror. So if the coating is on the front, then the only thing that's happening is that light rays coming, it's being reflected directly, and that's it. But if the coating is on the back side of the glass, right, what's happening is that first of all, light's coming in, it's coming in from the air into the glass. So you can see over here there's a bit of refraction happening. Can you observe that? Is it noticeable?
Yeah.
Right? I'll zoom in a bit. Okay. Then what happens, it hits the back side of the glass, is reflected, and then, right, it's traveling out, right, but some of it is being reflected back in. That is, right, hitting the silvering at the back. It's being reflected again and then traveling out, and so you've got these, right, multiple reflections happening just from, a single object, light from a single object, right? And so because there are multiple reflections happening, that is why you get this sort of a blurred image.
Yeah.
Simple.
Yes.
Right, so they mention that the these blur the right, so right, which is formed by one reflection at the silvering, especially if the glass is thick. The problem is absent in front silvered mirrors, but such mirrors are easily damaged, so there is, like, a problem with that as well, right? But anyway, then they talk about totally reflecting prisms. So, right, you can use 45. Have you ever seen prisms? Have you ever used prisms? These
No.
glasses, these chunks of glass at 45 degrees, right? So if you're using a 45-degree right angled glass prism, the critical angle of ordinary glass is about 42 degrees, and a ray of light falling on the face PQ, so over here, right, P and Q, because it is coming in perpendicular, just like the normal, as we talked about, it will not be refracted, right? So it's coming in at 42. So the critical angle is, sorry, 45. So the critical angle of glass is about 42, and a ray of light falling on such a prism hits at 45 degrees. And so total internal reflection occurs and the ray is turned to 90, right? So 45 degrees and then 45 degrees over here. And so the ray is bounced by 90 degrees, right? Why is this happening? Understand the concept. There are two things happening over here. If it's clear in my verbal explanation with the image in front of you, fine. Otherwise, we'll go to the whiteboard. All right, zoom in a bit more. The ray is falling perpendicular to the surface of the glass. That means it will not be refracted while it is entering the glass. Clear?
Yeah.
Right? It is hitting the glass surface at 45. So the angle of incidence over here at this point, right? The normal is perpendicular to this slant of glass surface. And so the angle of incidence is 45 degrees. Okay?
Okay. Yeah.
What is the critical angle? The critical angle for glass is 42 degrees. So any angle of incidence above the critical angle will cause total internal reflection. We just talked about that. And
Yeah.
so 45 degrees is larger than 42 degrees. That means that what's happening in the prism is total internal reflection, right? And so in that case, the angle of incidence is equal to the angle of reflection, remember?
Yeah.
Or the angle of reflection is equal to the angle of incidence, the other way around, right? And so you've got light coming at 45 degrees because the critical angle is 42, and so total internal reflection will take place, and so it will be bent a further 45 degrees, and so 45 and 45 is 90, and so right, it's moving out again perpendicular to this surface, this boundary. And so again, right, even though it's moving from glass to air, there'll be no refraction taking place because it is moving along the normal of this surface over here. Don't confuse it, this surface. And so what you're doing is basically you're able to turn the direction of the right light ray by 90 degrees.
Okay.
Does that make sense?
Yes.
So be it.
Yeah.
You need time to digest that, right?
Yeah.
Okay. Right. And so light can also be reflected through 180 degree by prisms, right? And that is depending on where you are throwing that light. So you got the same prism, but this time instead of coming in from here, you've got light coming in from here, right? And so again, this light is this ray of light is perpendicular, right, to this surface over here, and so it will not be refracted. It goes in 45 degrees, which is greater than the critical angle. You've got total internal reflection happening one, so that's a 90-degree change. Total internal reflection happening again, so that's another 90 degrees. 90 is 180. And so you're basically flipping the light ray around, and it is exiting the prism perpendicular to, right, the boundary, so no refraction happening. And so what you are achieving is a 180-degree flip in the direction of the light ray,
Okay.
right?
Yeah.
Then you have, light pipes and optical fibers. So you've got this pipe, right? It is curved, it is a curved glass rod, and so when light hits inside, it is undergoing multiple reflections, right? Light can be trapped. So when you said light is trapped inside, yes, that is put to use,
Yeah.
right?
Okay.
So light can be trapped by total internal reflection inside a bent glass rod or pipe along a curved path. So light's coming in, this is closed, right? And so there's total internal reflection happening multiple times, as many times as it hits the surface, right, until it doesn't exit. Okay.
Okay.
And so this kind of material is called an optical fiber, right? Or at least an optical fiber is an example of where this technique is put to use, right? And so several thousands of such fibers are taped together to form flexible light pipes that can be used, for example, in endoscopy. And I don't know if you've ever seen this, at least on TV in medical drama or something, that they put this, what we called camera, inside a person's throat to check what's going on inside, right? And so, right, they have a light source, and that light is hitting the walls of the internal, this is probably the esophagus, right? So it's hitting the walls of the esophagus, and it's being bounced back, and it's being captured into the optical fiber, and that is how the doctor is viewing it on screen. Okay. That's not the only use, right? It can also be used by engineers to light up some awkward spots for inspection. Right, so this is just for you basically to understand how this concept is applied in different scenarios. Right,
Yes.
and so increasingly optical fibers are being used to carry telephone, high-speed broadband internet, and cable TV signals as pulses of visible or infrared light. The advantage is that it uses light to allow information to be transmitted, which is much faster than electricity, right? And much more secure because the cables are unaffected by electronic interference and they do not corrode. So you have cables underwater, for example, copper cables, they might corrode, right? And so that's not happening. They can be used over long distances, they would cost less, right? And they can be made of cheaper material and they are lighter and thinner, so they're easier to handle, but right, they're not as strong, and so they can break if bent too much, right? And that is something that we over here experience every now and then, right? When the internet is lagging all over the country and they say, oh well, there's a problem with these submarine cables, and we need time to fix it. Did you get all of that?
Yeah.
Are you sure?
Yeah.
Yeah.
Okay, so that brings us to the end of this chapter actually. And next up is lenses. Ready?
Yeah.
Or would you like to take that break now?
Yeah. I would like to take that break now. Yeah.
Okay, so we'll be going on a 5-minute break and then I'll see you guys again after and we'll continue with the next chapter.
Okay.
Okay?
Yeah.
All right.
Should we stay on the call?
Yeah, we'll end the call. We'll rejoin after.
Okay.
Allah Hafiz.
Allah.